Okay, good evening to all. Today is the second webinar talk entitled Advanced Technique and Characterization with Spectroscopy Instrument, Principle and Application under Series 5, Advanced Technique and Development in Biomaterial Characterization and Application. Today we got two speakers. Let me introduce our first speaker today. Okay, our first speaker is chemist Dr. Hayrie Atta. Is a chemistry lecturer from Asia Metropolitan University, Johor Bahru campus. He obtained his PhD in 2019 from UTM and his academic experience in chemical sciences with 5 years research and analytic experience as well as in spectroscopy and chromatography. He is also a professional chemist registered with the Malaysian Institute of Chemistry, IKM. He published his work in ISI, WS, Corpus, and has numbers of collaborators from industry and universities. And currently is acting director, Center for Research and Development Program Coordinator, Foundation Science Program. His niche area and expertise is in organic chemistry, green chemistry, and material sciences. Without further ado, let me welcoming Dr. Mohd Hayrie for his talk. Doctor, the screen is yours.
Hello, good morning. Yeah, can you hear my voice?
Yes, doctor, I can hear your voice.
Okay, let me share my screen.
Okay.
Okay, can you see my screen?
Can doctor?
Okay.
I can see. Yes.
Very good afternoon to all of you. So thank you, Mr. Morgana, for the brief introduction. So today I would like to present my some topic on the application of the diffuse reflectant ultraviolet visible spectroscopy, especially in the material characterization. So I'm Hayrie Atta. I'm currently an acting director for Center for Research and Development at MU Medical Campus, Johor Bahru. I'm also a chemistry lecturer and as well as the program coordinator for Foundation in Science program. Okay, so let us, before we move to the DRUV-based spectroscopy, so let us recall back on the basic theory, what is the ultraviolet visible spectroscopy. So basically, the UV spectroscopy is based on the electronic excitation of the molecule. So the light from the UV or visible supply the certain amount of energy, which is equivalent to the gap between the ground state and the excited state. So when the electron absorb the light, so it will excited to the excited state. So this is the basic theory on the UV spectroscopy. So according to the molecular orbital approach, the absorbed energy of light is used to transfer an electron from bonding or non-bonding molecular orbital to an anti-bonding molecular orbital. So for example, in acetone, so all single bond here is the sigma bond. So while the double bond here is the pi bond. So the lone pair here is the non-bonding electron. So now the electron that transfer may be a sigma bond electron or a pi bond electron from the lone pair, and there is non-bonding electron, this one. Okay, so the possible electronic transition that are involved in the ultraviolet and visible region are sigma to sigma star, sigma to pi star, pi to sigma star, pi to pi star, and to sigma star, and to pi star. So basically, pi to pi star involve a compound containing the bond, and to sigma star involve compound containing the heteroatom. And sigma electron basically are held very tightly, thus require absorption at very far UV region for sigma to sigma star transition to happen. So basically like alkane saturated compound, so it won't be detected lah by the UV-based spectroscopy. So these are some of the application of the UV-based spectroscopy, which is identification of inorganic and organic species, quantitative determination of different analytes, identification of unknown compound, identification of polycyclic aromatic compound, elucidation of structure of organic compound, for example, vitamin A1 and vitamin A2. So this is typical diagram of the UV-based spectroscopy and the Beer-Lambert law. So light source, we have a sample here, and then the detector will detect the transmitted light. So at the end, it will record in terms of the spectra. So it basically on the Beer-Lambert law here. So absorbance equal to repulsion, which is a molar absorptivity of the absorbing species, path length, and the concentration of the absorbing species. So this one is for actually for the sample solution. So, but how about if the sample is in solid form? So we know that the semiconductor for biometrical applications such as the carbon nitride, titanium dioxide, zinc oxide. So these are the three the semiconductors that have an application in the biomaterial. So for example, carbon nitride application as the biosensor, titanium dioxide has been used as the antibacterial drug delivery, bone implant, and the zinc oxide, so application as anti-diabetic, antibacterial, and bioimaging. Okay. So, for example, the application of the titanium dioxide in the biomedical application, biomedical field. So the purple field here is a titanium dioxide. So when it receives the light, so the electron will be excited to the excited state, and thus the photocatalytic reaction happen. So it produces the superoxide and the hydroxyl radical. So this hydroxyl radical and the superoxide will then attack and destroy this bacteria. So basically it is based on the photocatalytic reaction. So what is a photocatalytic reaction? So for example, so semiconductor, it has a band gap. So the band gap, like such as a TiO2, it has a conduction band and the valence band. So the different semiconductor will have a different band gap energy value. So the so the electron at the valence band here, so it require energy. So the energy is a photon light, for example. So when the electron absorb the light, the equivalent to the band gap energy, it will excited to the excited state. So when the electron excited to the excited state here, the oxygen, for example, will receive the electron and to reduce to superoxide. So this superoxide will then proceed to the chemical reaction. For example, to destroy, attack the bacteria, conversion to the non-harmless compound like carbon dioxide and oxygen. And at the bottom part, we have oxidation reaction. For example, the water will oxidize to the hydroxyl radical by providing the electron here. So we basically can calculate the wavelength of light based and also the band gap energy based on this equation. E equal to hc over lambda. Okay, so h is Planck constant, c is speed of light. So for example, you want to know what is the wavelength related to the band gap energy. So for example, like you have a wavelength of 280 nanometer, for example. So you just insert the equation here and then you will get the band gap energy. Right? Okay. So for example, characterization of the material. So you have a research question like, you successfully synthesize the modified metal oxide for application of antibacterial invisible light. So we know that the titanium dioxide is basically active in the UV light. So now you modify the titanium dioxide to active in the visible light. So the question here, so how do you confirm that the material you have synthesized is exactly the titanium dioxide? Then second question, so you modify the band gap size of the material in order to work in the visible light wavelength. So how to determine the new band gap energy? Okay, so we have basically many methods for characterization of the material. We have SRD, DRUV-based, fluorescent, FTIR, EIS, This one, BET, SAM, FISAM, EDX, sensation analyzer. So you have to choose which the characterization method that will answer that question. Okay, so how do you confirm that the material you have synthesized is exactly the titanium dioxide? So you can confirm that the material that you synthesize is titanium dioxide based on the absorption range. And also you can determine the new band gap energy based on the dot plot. So this question can be answered by the DRUV spectroscopy. So basically UV spectrum lies in the range of 200 and 800 nanometer. So UV is 200 until 380 nanometer, and 380 nanometer and above until 700 is basically a visible range, and after that is a infrared region. Okay, so what is the RUV spectroscopy? So it is basically the study of the diffusely reflected photon, then specularly reflected photon, because the light is reflected internally. So it is based on the principle that not only does the light reflected from the material come from the surface, but some is reflected internally. That's why we call it a diffuse reflected. So as you can see here, the specular reflectant directly reflect off the surface, while diffuse, it penetrates into the sample, resulting in the scattering reflected light. So combination of both specular reflected light and the diffuse reflected light, we have the total reflected light. So here, type of the reflection measurement, we have specular reflected light, for example, like thin film, mirror surface, metal, diffuse reflected light, powder and paper, and specular diffuse reflected light for plastic and paint. So I will be focused on the diffuse reflected light because of most of the material we have in the powder form. Okay, sorry, I'm not basically a salesperson for Shimazu, but these are some of the spectrophotometer that you can choose depend on the information that what you need to get later. So we have the cheapest one here, just for liquid sample. So I was using this instrument. It can measure solid and liquid sample. So if you want to measure up to the near infrared region, you can choose this instrument. So here the sample of the UV-vis, the RUV-vis spectrophotometer. So this is the instrument there. So integrating sphere compartment, so you can take out and insert. So in order to replace, you want to choose solid sample or liquid sample. So typical diagram of the RUV-vis. Okay, so here I won't talking much on this, but I want to show you the integrating sphere here. So basically current the RUV-vis will be include the integrating sphere. So basically what is the function of the integrating sphere is to measure the total light radiated in the all direction from a lamp. Okay, now we move to the sample preparation and measurement. So basically you need to have a consistent amount of sample for each measurement. So it's good to have a reduced particle size in order to reduce the specular reflection. So if you want to fine powder, you have to grind. Because of the small particle size will have improve spectra. So barium sulfate, because it's a white color, so it used as a reference. So the range is 200 and 800 nanometer. It depends on the instrument, and also it depends on you as well. Because if you know that your sample is absorbed up to 200 to 400 nanometer, for example, okay, so you can just select the measurement range. So you don't have to wait a longer time in order for the machine to complete the measurement until 800 nanometer, for example. So the raw data that basically you will be getting there is a reflected mode. So then you need to convert them to the km. So km stands for the cubic amount, which I will talk that later. So here's for example, a raw data for the UV-vis, the RUV-vis spectra. This is reflected. So this is the sample of carbon nitride. So you can see that this one is low reflectance. That means that the carbon nitride absorb much in this region compared to this wavelength or region. So high reflectance means that sample did not absorb much in this region. So you need to convert the spectral diagram reflectance to the Kuebec-Kamang function or Kuebec-Kamang, depending on how you pronounce it. Okay, it is based on the Kuebec-Kamang theory in 1931 because it accounts both absorption and the scattering light effect. So that's why we have to convert to Kuebec-Kamang, so in order to get more accurate data. So in liquid sample, for example, it just for absorption. But in solid sample, because of we have the scattering effect, scattering light scattering, so it account for the scattering coefficient. So that why to have more accurate data, then you have to go for the to convert to the Kuebec-Kamang function. Right. Okay. So basically, in the REV base is based on the qualitative analysis rather than the quantitative. So qualitative is basically is what is that. So quantitative is how much the sample concentration, for example. So in the R, we are focused on the qualitative. What is that? What is the bond, for example? So in this graph, you can see that. Okay. The sample, for example, this carbon nitride prepared in 6 hours have a very high intensity compared to others. So this is because of the inconsistent amount of the sample. Okay. So the solution is you have to weight every sample. So for example, 1 gram for each of the sample, for example. But you need to know that there is some limitation. For example, like 1 gram of carbon nitride does not similar to 1 gram of titanium dioxide. Okay, so how to solve that? So we normalize the spectra. So why you need to normalize the spectra? Basically because of when spectrum is changing in its shape is, for example, like blue shape, we have a red shape. So basically blue shift is the shift to the lower region, lower wavelength region. The red shift is basically to the longer wavelength. And then pick our shifting on the wavelength scale. This one, number 2. So how to normalize the spectra? So you paste the raw data in the Excel, the original one. You find the highest value for, okay, for example, this one is 1.8. So you paste on the next column and then you divide with the original value. And then the Excel will calculate it for you. So here the new normalized point, and then you copy both, and then you save as a new data. Okay, this is the new normalized spectra. So the highest is 1. So the label can be excluded since it is normalized. So this is comparison between the before normalized and the normalized. Okay, so basically it provides clear spectra for in detail explanation, clear image of spectra shift, blue shift or red shift, and then the increase intensity, you can have more discussion on the scientific explanation. So rather than the technical. Okay, now we move to result and discussion. So this is sample of graphitic carbon nitride prepared in various salt meth. So the salt meth is potassium chloride, zinc chloride, potassium chloride, sodium chloride, and potassium chloride, lithium chloride. This is unmodified CN. So you can have a discussion like, okay, for example, this one, the less intensity, you can see that it can be due to the formation of defect. So when the defect form, less bonding of the C double bond N, for example. Okay, you can discuss clearly on the spectra shift for this example. So preparation in the different salt meth cause the red shift, for example. So the red shift can come to because of the decrease in the crystallite size, for example. Okay, so in addition, you can also combine the data, or you can have for example, layered stack. Okay, it's after all depend on how you're going to discuss the data. So for example, I choose this one to present it by stack because it will be easier for me to identify for example, this one, I want to identify the tetrahedral titanium, this one for octahedral titanium. So after all, it depends on you. So which type that you think that it might be easier for you to identify, to investigate the spectra. Okay, case study. So how the DREV-based spectra can be used to confirm your finding. So example one, so extending absorption of the material to longer wavelength. So if you can see that the natural sunlight consists of visible light, 45% of visible light compared to ultraviolet, only 5%. Okay, so now because of the natural sunlight consists of 45%, so you want to fully utilize the natural sunlight. So you have a very good, for example, photocatalyst, active in visible light, average band gap of 2.7 electron volt. But the carbon nitride is only absorption up to 460, 470, depend on the precursor. So now, because of you want to utilize the sunlight, okay, so you need to extend the absorption of the material to the longer wavelength. So how do we going to do that? Okay, so for example, so you can modify or doping, in this case we call it as a doping. So we dope the 2,4,6 triaminopyrimidine to the graphitic carbon nitride, TAP, because it gives the visible light absorption up to 700 nanometer and structure similar to melamine and so on. So now you have already, sorry. So now you have already doped the TAP into the carbon dioxide. So how the DREVV spectra can be used to confirm your finding. So this is the finalized data result. Okay, so you can see that the incorporation of the TAP into the CCN successfully extended the absorption to the longer wavelength, because we know that this dopant have the absorption up to 700 nanometer. So by doping into the carbon nitride, it has extended the absorption range to the longer wavelength. And then the upshift here, okay, we can conclude that the successful incorporation of the TAP into the CCN. Mana nak buat ni? Okay, so example 2. So you want to narrow the band gap size. So for example, like TiO2. So titanium dioxide is a very good photocatalyst, famous, and have a major application in basically in the photocatalysis field. So but the titanium dioxide has a band gap, wide band gap energy like 3.2 electron volt. Okay, so it's a very wide band gap. So now you want the titanium dioxide to be active under visible light. So you have to reduce the band gap. Okay, so basically it's to be active in visible light to reduce the recombination of the electron, because when the recombination of the electron happen, the photocatalysis won't happen. Okay, so common method like doping of non-metal metal to the Ti2 lattice. Okay, this one is the titanium dioxide lattice. You can see that the doping of the nitrogen into the Ti2 lattice. Okay, so the question is how to confirm or how to know that it has the new doped titanium dioxide, okay, has a new band gap energy or reduced band gap energy. Okay, so this one is the black spectrum is the titanium dioxide, and then the red one is the modified carbon, modified carbon titanium dioxide. So you can see that it has an absorption in the visible light. So you can conclude that the carbon already improved the absorption of the TiO2. So that means that this sample, okay, sorry, this modified titanium dioxide active in the visible region because it has absorption in the visible light, okay, and also a red shift. So that means that it active in the visible light. So now you narrow the band gap size. So how to exactly determine the band gap value? So you can converting the DREVV spectrum to the dot plot. Okay. So for the x-axis, you convert to 1240. So basically it's h times c, Planck constant times the speed of light. Okay, divide with x, and then you convert the y-axis to this equation. Okay, so you have to note about the coefficient here. So you have to know that your sample either is direct transition, direct forbidden, indirect, or indirect forbidden. Okay, so this is the top plot of the TiO2 and the carbon TiO2. So you can estimate the band gap value by extrapolating, okay, the line to the x-axis. Okay, so in this case, the TiO2 anatase has an average has a band gap of 3.4, and the modified carbon TiO2 has a new band gap of 2.9 electron volt. Okay, so basically TiO2 has an average band gap of 3.2 electron volt, but because of different precursor, different synthesis synthesis procedure and so on, it might lead to a different value. Okay, so change in the particle size. Okay, so for example, in this, we have three types of the crystalline carbon nitride, CCN, calcine in the different temperature. So basically on this result, so we can conclude that the increasing calcination temperature led to the red shift, while decreasing the calcination temperature led to the blue shift. So the blue shift and the red shift, okay, as you can see here, can give you information about the change in the particle size. Okay. Okay, so decreasing the particle size, particle size will lead to the high band gap. Okay. So for example, smaller particle size has a high band gap value. So that is why it appear in the blue shift. Okay. So the blue shift mean it absorb in the shorter wavelength, so that means that it requires high energy in order for the electron to be excited to. And then example 4, so you can use the data information from the DRUV base in order to propose a mechanism in the photocatalytic reaction. So for example, in this case, incorporation or doping of TAP into crystalline carbon nitride. So after doping the TAP into the crystalline carbon nitride, so we have improved absorption edge. For example, that CCN previously have a 490 nanometer. So after dop with the TAP, it improved the absorption in the visible light. Okay, so it improved to 510 nanometer. So now you convert it to the dot plot in order to get the band gap value. So for example, CCN 2.6 electron volt, CCN TAP 2.4 electron volt. So you know that the incorporation of the TAP into the CCN has reduced the band gap energy of 0.2 electron volt. So basically, based on the data that energy band gap value you obtain from the top plot, you can propose a mechanism in the photocatalytic reaction, for example. So the conduction band here can be obtained from the EIS spectroscopy. So now you have a 2.6 electron volt here for the CCN, and then you dot with the TAP here, you have a new band gap energy, which is 2.4 electron volt. So you just calculate the band gap value in order to obtain the conduction band position. Okay, this is important because of the standard reduction potential of the oxygen. For example, in order for the oxygen to be reduced to the superoxide, okay, sorry, it must have the band gap, the conduction band must have a much more negative value compared to the standard reduction potential of the oxygen. So this band gap energy value can help you to determine the proposed mechanism. So for example, the valence band, it must have a positive value, positive position compared to the standard reduction potential of the oxygen to water, for example. If the position is higher than the standard reduction potential of the oxygen, okay, so the oxidation will not be happen. Okay, so example 5, charge transfer or DD transition, you can also obtain the information from the UVB spectra. For example, this one is the doping of chromium into the titanium dioxide. Okay, so the absorption in the 600 and 800 nanometer account for the DD transition of the chromium from 4A2G to 41G, and then it also CR3 plus to the Ti4 plus Ti titanium tetrahedral species, and then at the 450 nanometer for the 4A2G to 412G of the chromium 3 plus. Okay, so different energy level will have a different excitation, different wait okay, so different transition, DD transition will have a different band gap energy. So this is why the 400 this is why for the 4A2G to the 41, so it happened to the 400 nanometer and above. Okay, because of the energy band gap energy, the gap is large here. So basically from this spectra, you can conclude for a mechanism about how the photocatalytic reaction work. Okay, for example, you have the absorption at the 600 and 800 nanometer. You will have a CR3 plus to the Ti4 plus. So you can conclude that is a excitation on the line here stand for the CR3 plus excitation electron from the CR3 plus to the conduction band of the TiO2. Okay, so and then CR3 plus to the Ti4 plus at this position. So the excitation of the electron, okay, so you see that the gap is small, so that is why it appear on the very long region. Okay, some considerations that you need to consider when you analyze, so when measure the RUV spectroscopy. So if the absorption peak is not well resolved, it will be difficult for you to estimate the band gap energy and can lead the erroneous conclusion. And the sample must be relatively inert and stable toward radiation and the temperature fluctuation and have a good aging properties. And then the identification of individual component of compact mixture can be extremely challenging, owing to overlapping of band and the presence of several absorption from the same functional group. So you need to do a devolution method. And then quantitative information may be hard to extract from the spectra. Okay, I think now already 3:30, so thank you very much. So if you have any question, you can just ask in the comment section.
Okay, thank you, Dr. Hayrie, for very informative talk. Now we move to our second speaker.